checked it out. So now it's time to get out into the wild blue yonder. And now it's time to get crazy. So the dark matter then must be made of something that, well, it certainly interacts by gravity. And we can hope and think and postulate that it might also experience the weak force. So maybe it is a weakly interacting massive particle, or a WIMP. So you might have liked to think that the dark matter was made of machos, but instead it looks like we're dominated by WIMPs. How humiliating. Bummer. But there's more bummerdom to come, because there's only one WIMP that we know for sure actually exists in nature, and it's the neutrino. And actually it was realized as far back as the 1980s. And the guy who employed me is a postdoctoral fellow, Simon White, very good astronomer, a great theorist, and contributed a lot to observational astronomy as well. And he studied back in the 80s, back before I ever met him, the consequences of a universe dominated by neutrinos. And here's the thing about neutrinos. Neutrinos, they move really fast. So we have to talk about a different way of classifying the dark matter before we go further. So there's a different strategy for finding out what is the dark matter. And the strategy is talk about, in effect, the temperature, the speed, the motion of the dark matter. So we say that either the dark matter is hot, meaning it is moving very rapidly, it was born, and it still has a very fast velocity, or it could be cold. Cold dark matter would be made of something that only has velocity because it's been pushed and pulled around by local gravity. But it was born with essentially no velocity and then just acquired some by being in a galaxy or in a cluster or something, and so it might be moving at speeds that are typical of stars, for example, but not moving at the speed of light, okay? Or something in between. We could call it warm dark matter. And whether it's hot, cold, or warm affects how structure forms in our universe, in our whole universe. So we're going to now talk about hot dark matter, cold dark matter, and warm dark matter. And to bring me into a little bit, we'll even talk briefly about mixed dark matter, because there's a story there. So hot dark matter is particles that have a high random velocity, in addition to the normal expansion with the rest of the universe that we talked about, the Hubble flow, and any galaxy or any velocity that they were born with. That's hot dark matter. Okay. Yeah, okay, I'm just going to move on. So, what hot dark matter candidates, elementary particles, could there be? Well, you could perhaps come up with other candidates, and you could go crazy there, but you don't need to, because we already have one, and we know it exists, and we already know that the dark matter can't be hot, just to cut to the chase. So the neutrino is hot dark matter. They're very, very high energy, and yet they're extremely low mass. The current estimate on their mass is somewhere in the, the range of 1/10 of an electron volt, or maybe less. There's different kinds of neutrinos. There's electron neutrinos, there's muon neutrinos, and there's tau neutrinos, and they're all zipping around. Could they make the dark matter? And here's how you realize that no, they can't be. So these are moving at speeds that are so rapid that the only things that could begin to separate themselves out from this expanding early universe, the Hubble expansion that we still see today, is things that were so big that the free streaming of these neutrinos couldn't outrace it. So things like things on the size of large clusters of galaxies, or even clusters of galaxies, are so-called superclusters. We haven't talked about superclusters, but if you look off in the sky, you can see that, gee, there seems to be more clusters of galaxies in this direction and not so many off in that direction. And it does look like superclusters statistically do exist, although the statistical clumpiness of them is pretty weak, but they do seem to exist. These would be the first things to separate out. And then only later, after velocity sorting had kind of had all your neighbors moving at roughly the same speed as you are, or they wouldn't still be your neighbors, would have the local speeds, and compared to your local standard of rest, be slowed down enough that maybe then you could make a cluster of galaxies. And then only later, within that cluster of galaxies, could velocities get low enough from the dark matter, which again is what the dominant matter is, be slow enough to make individual galaxies. And then only then, within individual galaxies, could you hope to begin to make stars. So in a universe dominated by hot dark matter, the youngest things, the things that formed yesterday, would be stars. And the oldest things would be the superclusters. And if they're very, very old, then they would have plenty of time to get very density contrasty, to show themselves by being very, very clumpy. And stars would only just be beginning to form out of the gradual gas and dust in the galaxy. Okay? So this is a so-called top-down scenario. Structure built chronologically, from big down to small. Now, how does that compare with the actual universe? It is in violent contradiction. This is not at all the way the universe really looks, not even remotely close. The universe we see is dominated exactly the opposite. The oldest things that we can see are stars. Okay? I mean, we're not going to go back to the first few years of the Big Bang. We'll do that later. But again, we looked at globular star clusters, and we looked at the stars inside dwarf spheroidal galaxies. And those stars, those clusters, are almost as old as the whole universe, 13.7 billion years old. And galaxies, even, are pretty clumpy, so they formed relatively old as well, 2 billion years after the universe itself. It's the clusters that look not very clumpy, and the superclusters that are barely detectable at all. So we live instead, clearly, in a universe that is built bottom up. It's the densest, well, the smallest things are the things that formed first, and the biggest things are the things that formed last. And that tells you that the universe is not dominated by hot dark matter, it's dominated by cold dark matter. Okay? So there's the key thing, first key thing, or certainly a key thing to remember about dark matter. Whatever it is, it's cold. It is cold dark matter. Some people still try to see whether we can maybe squeeze in a little bit of warmth there, but frankly, even that is looking less and less likely, as well as being theoretically a little bit ugly. We don't need warm dark matter to account for everything we see. We don't know of any warm dark matter candidates. We want to be diplomatic. We want to be open-minded. We want to keep the door open a crack just in case. But, to tell you the honest truth, which we always tell you to do, give you the correct, best probabilities of what's true and what's not, and the probability of warm dark matter looks pretty low. I would not bet much money on warm dark matter. Cold dark matter. It's also nice and simple. We know that it has to be pretty darn cold. We know it's out there. And so maybe the universe is actually simple here, and there's really just one cold dark matter particle that is accounting for all this. So I use the word particle. Do we really know it's a particle? Well, at least it's not big enough to be self-gravitating. And if it only feels the weak force, it's hard to see how it could be clumped together and bigger than anything other than an elementary particle. So the candidates we're going to begin to look at are really elementary particles, but they're elementary particles that are not hot dark matter. They are cold. Okay? They acquired their velocities by being pulled on by gravity over the 13 billion years that we've been hanging around out there and getting clumpy. Okay, so here's the problem, though, with cold dark matter. There aren't any cold dark matter particles that we know for sure actually exist. I know, that sounds terrible. And it is kind of terrible. But you have to turn that frown upside down and say, well, gee, that makes it a nice mystery. Now we've got a mystery to solve. We can figure it out. Now, back when I was working on this in the 1990s, all of my compadres and I too would have thought, gee, what do you think? By 2020, are we going to have discovered what the cold dark matter is? I think all of us would have put some money, a little bit of risk capital on, yeah, we'll figure it out by then. Technology's getting way better, and we got some ideas, and we know how to test them. We're going to be doing the testing. Yeah, we'll figure it out. I'll bet you we'll know what it is. Well, here we are in 2020, and, well, I'll save that for later, whether we know what it is or not. Now, it's going to get pretty wonky from here. I might have to go over a lot of purple slides. There's a limit to how much I'm going to expect you to know on the details of these, but, it's a pretty interesting subject. Okay, let's put a slide in here on warm dark matter. So what is warm dark matter? It would be something that has some primordial velocity, enough to kind of blur out the smallest things that we know are dominated by dark matter. So the smallest things we know that are dominated by dark matter are the dwarf galaxies, the dwarf spheroidal galaxies. But as near as we can tell, the structure of the dark matter, as revealed by the velocities of the stars in those clusters, still fits pretty well with cold dark matter. There was a time when we thought maybe we needed a warm dark matter, but in fact it was just a limitation in our technology and our ability to detect these things. There was a thought, and there's still a few people who are thinking or hoping, let's say hoping, that maybe there's warm dark matter, and the evidence would be there aren't enough dwarf spheroidal galaxies. But now remember how you make a dwarf spheroidal galaxy. This is from the last chapter. And the way you make them is you have stars and gas and dust mostly gas and dust come together and make some stars, but then some of those stars are massive and they blow up as supernovae. And because the mass of these things is so weak, even with the dark matter, is so weak that they actually blow apart. And all of the gas and the dust gets blown out. And that shuts off your star formation. So now you have very few stars. So it's pretty natural that there would be a minimum. It's about 10 to the 8th, about 100 million solar masses, that you would expect to see stars at all in these things. And below that, you'd expect that even the first generation of stars would be so inhibited by this mechanism that you would, just not be able to find them. So warm dark matter doesn't really have a strong case for it at the moment. Okay, so what is a dark matter? Well, we think it's some elementary particle. So we just talked about that and why we think that. How can we try and detect these things? Could we detect them directly from the ground here? Or do we have to go out into space to try to find them? Well, there is one place where we're trying to discover them, and that is in the most powerful particle collider, okay, the Large Hadron Collider, the LHC, at CERN in Switzerland and France, kind of both at the same time. It's a big detector. And we're trying to see whether we can create cold dark matter candidates. Okay, so we need some candidates, though. Let's talk about what are the candidates for cold dark matter and explain the constraints that limit us to these candidates. The constraints. The particles have to be essentially dissipationless. So what does that mean? That means when they fall together into a gravitating thing, they can't squish against something and then just parachute themselves down to the middle. They may have been born with low velocity, but if they acquire some velocity by gravity, they're not going to be able to get rid of it. So you would expect then that the density profile would show a roughly 1 over r squared fall off. And that would tell you they're essentially dissipationless. They're not like hydrogen. Hydrogen bangs into other hydrogens, might form a H2 molecule that'll dissipate some of the energy of the collision, might form ionized hydrogen, but then you've got some radiation that's going to go away because their charged particles are going to wiggle the electromagnetic field, and that's going to carry energy away, and so again you're going to be able to dissipate. And that's how the gas in the disk of our galaxy formed, and that's how the giant black hole in the center of our galaxy probably formed, is through dissipation like this that enabled a lot of mass to get into a very small place. But we don't see it getting into quite that small a place at the amounts necessary. The fact that it falls off gently, relatively gently, like that, is telling us that it's probably dissipationless. It looks like it only feels the weak force, if that, and gravity. Doesn't feel the strong force, doesn't feel electromagnetism. Okay? Now here's some direct evidence for dissipationless that is on a bigger scale, and this is called the bullet cluster. And the two colors here are, the colors are added artificially later, but the meaning of the colors goes like this. So this is two clusters. A relatively big one here, clusters of galaxies. And these two clusters have run into each other. So this guy here, he came from over here. And he came in like this. And this guy, he came in from over here. I'm going to draw them from off center a little bit just so I don't put line on top of line. Okay? And so these guys actually went right through each other. Now you might say, well, how could they do that? Well, you know what? There's enough empty space that all the individual pieces, the stars and even the galaxies for the most part, they didn't run into each other. They just passed each other like kind of like on those freeway chase scenes, and Terminator and other movies where you're going the wrong way down a freeway and somehow you still manage to miss all the other cars. Of course, that's all CGI, but anyway. So where was I? The blue. Okay, the blue is trying to tell you where is the dark matter. This is the color demonstration of the mass distribution, which again is more than can be accounted for by all the stars. There's not enough mass in starlight and cold gas would also get blown backwards. But there's not enough mass in stars. The dark matter went right through. So the fact that there's a blue clump here, just as big as this cluster, and a smaller blue clump here, is telling you that the dark matter went right through each other and they didn't bat an eye. They didn't get dissipated at all. What did get dissipated is the gas. And that's what this is. This is now heated gas, the red. And it did feel each other, and so it did get knocked backwards. There's even a bow shock here, it kind of looks like. Okay? But the dark matter is not the gas, okay? Clearly these guys are way offset. So the bullet cluster argues that, yes, the dark matter is dissipationless. It needs to be stable. Here's another characteristic. Or at least stable enough to last for 13 billion years without disappearing. The stability of the proton is something we can now measure. The stability of the proton can be measured in a very interesting way. Take enough water, which has protons in it, and get enough water there and enclose it in a big dark sphere and put a whole bunch of very sensitive light detectors inside the sphere and wait for one of those protons to decay. So when it decays, it'll turn into lighter particles that are zooming off at the speed of light. It's going to create Cherenkov radiation. That's going to create light. Light from inside something that is absolutely opaque and won't let any light in. And that's how we detect the decay of protons. Now, 10 to the 34th years, you might say, Rick, the whole universe is only 10 to the 10th years old. How could you possibly measure the age, the lifetime of a proton to that kind of level? That's impossible. No, it's not, because this 10 to the 34th years is a random thing, just like all radioactivity. It's a totally statistically random quantum process. So all you need is to get 10 to the 34th protons together in one place, and you ought to have one of them disappear every year and see it produce Cherenkov radiation once a year. And then you could measure. And if you work it out, that's about what we got with the big Sudbury neutrino detector. It's there to detect neutrinos, but you know what? It could also measure the decay of protons. And if you go through a whole bunch more math, then you can even convince yourself that the standard model of particle physics looks like it has no new forces. The four forces of nature, that looks like all the forces we got. If you go back early enough into the early universe, maybe those unify into less forces, but it doesn't look like we have more. So the particle looks like it's got to be stable. Oh, so by the way, yeah, just to finish that. No, we haven't seen the proton decay. It's at least 10 to the 34th years between proton decays. Okay, wait a minute. The particles have to be cold, or at least cool. And we really already talked about that. Well, there's additional evidence we haven't talked about yet. Gee, we're only 3 minutes away from the end of class. I will continue for another 2.5 minutes. Clearly we're not going to get through all this chapter, but then you know what? I didn't expect to. We do pick this up next time on Wednesday. But we're going to look at the CMB, the cosmic microwave background. We haven't talked about that yet. But the cosmic microwave background encodes the lumpiness of the universe back at a time when the universe was way younger than anything born in our galaxy, way younger than the globular clusters that we've already talked about. And the lumpiness there is also telling us how cold is the dark matter. So, being cold allows the particles to gravitationally clump on all scales, even scales much smaller than typical galaxies. And we're going to see that the universe must have been lumpy, even back at 300,000 years after the Big Bang. And there's no way that the ordinary gas that makes up the stars could have been that lumpy when it was that early, because it was still too warm to do so, and there wasn't enough time for that gas to have gotten clumpy. The gas must have fallen into clumps and lumps that were already there. Lumps that were made by the dark matter, which doesn't dissipate and doesn't need any kind of help. It just falls together, and it can be the lumpy stuff right away, and the ordinary stuff falls into it, and it makes the microwave background lumpy. That's where we're gonna reiterate that again next time. But it is now 10:50. So I am going to close this program. So this is good. We got in good 73 minutes. That'll make a nice good YouTube video. I hope other people around the world and on other stars and galaxies who can access our internet will enjoy this presentation. I think it went pretty well. Does anybody have any last questions before I start shutting things down here? Sarah, Andrew, Abriel, Riley.